This video will explain the SimCLR algorithm from researchers at Google, which is the latest and greatest for unsupervised learning. SimCLR achieves the same performance as a ResNet 50 trained with supervised learning on the same dataset, although this comes at the cost of longer training time and larger networks. SimCLR uses contrastive self-supervised learning to leverage unlabeled datasets for representation learning. Self-supervised learning describes this idea of forming a supervised learning task automatically from unlabeled data, and contrastive learning describes the idea of training networks to have high similarity in their representations between positive pairs and inversely for negative pairs. Using contrastive self-supervised learning will help enable the next generation of computer vision and artificial intelligence because constructing labeled datasets like ImageNet on the scale of billions or trillions of images is intractable. A much better solution would be to figure out how to do representation learning without labels. SimCLR is a nice framework for doing this that explores the role of data augmentation functions in forming these pairs for contrastive learning, using a separate projection head from representation to the contrastive loss space, and then the role of scaling up unsupervised models with respect to the parameters, training time, and batch size. This video will give an overview of the details in the SimCLR paper. This video will explain the SimCLR unsupervised learning algorithm. Putting a simple linear classification layer on this representation learned from unlabeled data is able to achieve the same classification accuracy as a ResNet 50 trained with supervised learning. This slide presents an overview of some of the results of SimCLR. You can see that you can achieve the same classification accuracy as a ResNet 50 trained with supervised learning, but at the cost of more parameters. In this case, you're also using a ResNet 50, as in the depth of the network is 50 layers, but you're increasing the width of the network, or the number of filters that are in each layer, by 4 times to achieve this more parameters but high matching accuracy when training with this unsupervised learning task. So you can see the performance of previous contrastive self-supervised learning algorithms like contrastive predictive coding from DeepMind and momentum contrast from Facebook, and how well they scale up with respect to scaling up the respective model sizes as well. And you see that they also benefit from scaling up the model size. One of the key findings of this paper is that unsupervised learning algorithms benefit more from scaling up than supervised learning does. And then you can also see the performance of some other unsupervised learning algorithms like Big BiGAN, which is where you do this big GAN task of mapping the random vectors into a data points that match the distribution of the real data set. But then in the Big BiGAN, you're also mapping that back into representation and using that to train classification models. Rotation describes this task of taking unlabeled data points, rotating them randomly like 90 degrees, 180 degrees, and then tasking the neural network with predicting the rotation angle and then using that representation for ImageNet classification. So you see the performance of SimCLR highly exceeds previous algorithms on this unsupervised representation learning. You can also further see this in the tables on doing this linear classifier on top of the unsupervised representation that's learned, as well as semi-supervised learning where you fine-tune it on a small percentage of the data, and then transfer learning from this representation onto different vision image tasks. This table further shows the results of doing the unsupervised representation learning and then putting a linear classifier on top of the representation and then training that to do ImageNet classification. You see the achievement of 76.5% top 1 accuracy is really remarkable for an unsupervised learning algorithm achieved by SimCLR, as well as a 93.2% top 1 accuracy. For the sake of reference, the most recently released noisy student efficient net model from Google has achieved 88.4% top 1 accuracy on ImageNet, which is the state of the art for ImageNet classification at the time of releasing this video. You can see the comparison in models that are using the simpler ResNet 50 compared to say something like a EfficientNet or the reversible network, which is where you don't have to compute the activations in the forward pass sort of to save memory, or these custom architectures. And you see that the SimCLR really outperforms all these algorithms that are looking at using ResNet 50 as well as the custom architectures. Another interesting application of these kind of algorithms is semi-supervised learning. Semi-supervised learning describes a learning paradigm in which you have a massive data set, but only a subset of it is actually labeled. So say you go to web scraping and you take 100 million images off of the web for your respective classification task, but you only have time to label 1% of the data. These are some of the algorithms that are used to alleviate that problem and let you still take advantage of the unlabeled portion of the data set with respect to the subset of labeled data. So you see in the fixed match paper, which is a recent algorithm that came out from Google as well, they have in their paper, if you want to check it out, a section where they look at the results of supervised learning on that subset of the data compared to doing something like semi-supervised learning where you're also leveraging that massive unlabeled part of the data set. And it's just a massive difference between the performance of just supervised learning on the 1% of labels compared to doing some kind of semi-supervised learning algorithm. So in this case, the SimCLR training with the contrastive self-supervised learning task, and then you take that representation and fine-tune it on the subset of data, outperforms all of these previous algorithms for doing semi-supervised learning. Another interesting application of this representation learning is transfer learning. Transfer learning is usually described in the case where you take a representation that is trained by doing something like supervised learning on the ImageNet dataset, and then you take that representation and fine-tune it onto a dataset where usually you have less labeled data points. So the ImageNet dataset with something like 1.4 million labeled images, you then fine-tune it on, say, something like CFAR 10 that has about, I think, 50,000, or like the food dataset or Oxford Flowers, or one of these datasets that has less labeled data, and doing that kind of a transfer from the representations learned on the larger dataset into the smaller dataset is really useful. You can see the performance gains from supervised learning compared to just training on these datasets from a random initialization. So in this case, you see the SimCLR representation is outperforming or is on par with the supervised learning with respect to starting from that representation to then train on these datasets with supervised learning. Another interesting characteristic of the results presented in SimCLR is that they're doing their unsupervised representation learning on the ImageNet dataset as well, but you'd likely expect these results to improve if you ran the SimCLR on a bigger dataset. That's the appeal of these unsupervised representation learning algorithms, is that they can scale to any size dataset. So for example, Google is building this JFT 300 million dataset, and you'd imagine that if you did this SimCLR representation learning on JFT 300 million instead of ImageNet, you would see even further gains reported in the paper on SimCLR. You also might imagine doing something like in the recent ImageBERT paper from Microsoft Research. They have this kind of like a multi-stage pre-training framework where maybe you'd imagine doing SimCLR on the JFT 300 million, then ImageNet, and then fine-tune it on something like CFAR 10. And it could be interesting to see how these kind of scale looks with SimCLR. Now we'll get into the technical details of how the SimCLR is going to learn these representations from unlabeled data. The idea behind self-supervised learning is to construct a supervised learning task from unlabeled data. Particularly contrastive self-supervised learning is looking at these tasks that maximize agreement or compare the differences between positive and negative pairs. So in this example, the positive pairs are going to be formed by doing data augmentations on unlabeled data points. So say you sample this dog image, then you're going to augment it with one of these transformations, and that's going to form the positive pair, and the negative pairs describe all the other samples in the dataset as well as their augmented counterparts. The next idea in SimCLR is to explore the composition of these data augmentations exactly to see what order of doing these augmentations, what magnitude, the composition of doing like crop and then color distortion, how that impacts the performance of the representations learned by doing the contrastive loss. And the next idea is to separate the projection. So you take the raw augmented data point and you map it into the space h sub I with the representation function. So this F mapping is going to be what's transferred when you then do the fine-tuning with image classification. But what they're introducing in SimCLR is they say don't do the contrastive loss directly on this representation. Rather introduced another nonlinear, which means that this representation is going to go through like a ReLU function and two weight matrix transformations into this space z sub I, which is where you're going to apply the contrastive loss. You can see in this visualization of the difference between doing that, the H representation is clearly more separated in the TSNE visualization than this kind of a Z space is, because as they show later on in the paper and as we'll present in this video, the kind of contrastive loss results in reducing some information from the original representation. The next finding is that unsupervised learning benefits more from scaling up than supervised learning. This is manifested in the form of model size, training epochs, and batch size as well. And then also we'll look at their normalized cross-entropy loss with the adjustable temperature parameter, which is like where you apply that divided by tau in the softmax of this kind of a, like a distribution of doing the exponent of the similarity divided by the normalized of all of the different vectors. The first exploration in the SimCLR paper is to look at the composition of data augmentations and how ordering this impacts the downstream performance. You can see some examples of these different augmentations, like the original dog image, then doing a crop where you crop out this part of the image and then resize it up with probably something like bilinear interpolation to make it the same resolution as the original image. You can also see things like doing the color distortion or this cutout, which is kind of like drop out in the input space. Rotation, this is the task that's used in that other baseline self-supervised learning task where you rotate it and then predict the rotation angle. These are all examples of different augmentations that you can use to take this data point and then form its positive pair for the contrastive learning task, where you want to have the similarity between these points be more similar to, say, the image of this and like a bulldog image sampled from the same data set. The main workhorse of the data augmentation used in SimCLR is this kind of crop and resize augmentation. So the idea here is that you would crop something like the tail of the dog and then resize it to the original resolution of the image. So the idea here is that looking at different kinds of crop and resizes, you can see this global local view where you take something like the B, which is cut out, which is a bigger space of the image, compared to something like A, which might be just like the face of the dog or a more specific region of the image. You compared to an adjacent view where there's no overlap between the two cropped images that are then resized. This kind of idea of looking at different pieces of the image and trying to be consistent across the different cropped regions of the same image is another idea that's used in contrastive learning, particularly in this paper, Contrastive Predictive Coding, where they're are explicitly looking at these different cutouts of the image and measuring the similarity and trying to be consistent within the same image, and that's how they structure their contrastive learning loss function. This table is a nice visualization of the downstream performance from different data augmentation compositions. It's also interesting to note here that they're not putting the left half of this branch through a transformation as well. When they run the full SimCLR algorithm, the data point will be transformed twice into x prime I and x prime j. In this case, they're keeping this left half of the branch fixed, so it's the same x data point, and then they're experimenting with this side of the chart, which is the reason why these performances are slightly down from the final result. And it's also amazing to see that how different this is compared to the final results, even though I don't think this is with the 4 times width parameter on the ResNet 50, because obviously that would be more expensive for them to be training these like 600 million parameter image classifiers to do this kind of an ablation visualization. But still, this visualization is really interesting. You see, if you do a composition of just blurring the image, like if you just take this image and then you blur it with like a Gaussian blur, which is where you just like add noise to the pixels with like some kind of like a window, you get only 2.6% accuracy compared to the composition of doing like a crop and then color augmentation, which is 56.3% accuracy. The next key workhorse in their data augmentation pipeline to form these pairs for doing the contrastive learning task is color transformations. This image shows an example of it. You see the original dog image, and then you see some kind of change to the color space that results in a new dog image. They attribute this to the color histogram distributions with these classical kind of crops or these geometric transformations like rotations or say like a horizontal flip. You get the same color histogram. So even the only differences really are going to come from these cropping, where you get like a different distribution of the colors in the image compared to something like rotation that's going to have the exact same color histogram as the original image. So they attribute in their paper that these deep 600 million parameter convolutional networks will overfit to anything. They'll look at any kind of pattern in the data that they can use, and this might be something that they'll use in order to classify the images without actually learning a useful representation of like the visual world or whatever. So then they show the difference between when you use the color distortion and how you can change these color histograms such that the neural network can't just look for something like this, and it has to learn a more semantic representation of the data. And then the next finding is one of the key ideas in this paper is that larger models, bigger batch sizes, training for longer, and then having more data augmentation results in better unsupervised representation learning. So in this case, you see the scale up of adding more distortion to the coloring, like modifying the color space of this more dramatically results in better augmentations compared to the supervised learning, where the more strength in the color distortion, it actually starts to perform worse. Then you see the comparison with auto augment. Auto augment is like this data augmentation controller, which it's a reinforcement learning algorithm that trains itself to augment images as well as it can, such that the augmentations result in the best trained image classifiers. And you see that auto augment doesn't work quite as well for unsupervised learning. But you can also imagine maybe doing the same auto augment search controller with this SimCLR algorithm. The idea in the SimCLR paper is to have a separate projection head that takes this representation learn that's eventually used for the downstream fine-tuning on ImageNet or transfer learning or semi-supervised learning, and take this representation and then map it into a new space z sub I to do the contrastive loss. This table and this TSNE visualization further gives evidence for why you want to do this mapping from the representation H into G of H to do downstream tasks. You see a lot more entanglement between random classes. These are random classes sampled from the ImageNet and they're colored by their class. You see more separation done with the H representation compared to the Z representation that has to take on that contrastive loss function. And they also show the difference between fine-tuning from the representation for different tasks, which is the key idea of this, is that you want to fine-tune H, the representation before the G of H gets to the contrastive loss for downstream tasks like ImageNet classification, compared to the G of H space on different tasks like predicting if it's a color or grayscale image, predicting the rotation angle, or original versus corrupted, original versus Sobel filtered, these miscellaneous self-supervised learning tasks that are used as a proxy to evaluate the representation. This table further shows the results of doing a nonlinear projection from the H into Z space. The idea here is that the orange, yellow kind of nonlinear is where you take that H representation and you map it by transforming it with a weight matrix, then putting that through a ReLU function, and then putting that through a second weight matrix, compared to just say having a weight matrix times H is how you get this final representation. So you see the performance is better by doing the nonlinear projection head. Now that we have an understanding of the contrastive self-supervised learning task, the composition of data augmentations, and the separate projection head, we can walk through the pseudocode of the SimCLR learning algorithm. So the input is the batch size of the network, the temperature tau that's used to smoothen out the dot product similarity between these representation vectors z, and the structure of the neural networks f, and then the nonlinear projection from h to z, g, and then the data augmentation function tau. So the first idea is that you draw these two augmentation functions sampled from the augmentation function. So basically it would be like a different magnitude parameter of doing the cropping, and then the color distortion that would come from, say, this t sampling compared to t prime might be like the global view, local view, or like the different adjacent views, and then different magnitudes of like scrambling the color histograms by doing different like color transformations. So then what you do is you pass these augmented images. And it's also important to note that both of the positive pair images are augmented. It's not like the original data point compared with the augmented data point. It's two augmented data points compared with each other, as well as then the negative samples, which is just the rest of the batch. So then you pass it through these transformations, getting the H representation, the Z representation. Then you loop through the batch as well as the the augmented batch, and then you compute these similarity scores between all the Z vectors in the batch, and then it's smoothened out with this tau temperature parameter, as well as it's normalized kind of like the score of similarity between the vectors. So then you define the loss function on the positive pairs, and then you update the network to try to maximize the similarity between positive pairs. And I guess you kind of like minimize the similarity between negative pairs by increasing the similarity between the positive pairs, because it's normalized by this kind of similarity between all of the vectors in the batch. The next key finding in the paper is that scaling up model size, training steps, and batch size improves the performance of this SimCLR algorithm. So a quote from the paper is that unsupervised learning benefits more from bigger models than its supervised counterpart. So in this case, you see the difference between the supervised learning and how the performance saturates quicker. You see the slope of this line is smaller than the slope of this line with respect to scaling up the ResNet 50 width parameter with the SimCLR algorithm compared to supervised learning. And then differently, these red stars compared to the blue stars, blue circles, describe how long you've trained the network for. So the blue circles describe training it for 100 epochs compared to red is 1,000 epochs, and then green is 90 epochs of training. So you see that even though you get good performance with this unsupervised learning algorithm, it comes at the cost of bigger models and more training time needed. This plot further shows the results of scaling up the batch size and the training steps, with the farthest right plots in this chart being the larger batch sizes and the farthest left being the smaller batch sizes. And then you see as you increase the training epochs, you see this kind of an increasing accuracy. So further showing this idea that unsupervised learning is going to benefit more from scaling up the training than supervised learning does. Another interesting detail of the paper with respect to scaling up the batch size is implementing this global batch normalization. So as they train this with data parallelism, which is where you have a separate copy of the model on each of the GPUs, and they each receive a subset of the data to train on and then send the gradients back and do like a global parameter server update. What they do here is, if you have these local batch normalization layers on each of the GPU, they might learn these mean and variance statistics that bias them to the batch at hand. So sort of this idea of global batch normalization further reinforces this idea of having taking advantage of these larger batch sizes, and that unsupervised learning will benefit more from doing that, because they're all sharing these mean and variance parameters across the entire batch, such that they're better taking advantage of the larger batch size. If you're interested in checking out the paper, they have some further notes on the differences between these different contrastive cross-entropy and different loss functions that have been used in the literature on contrastive self-supervised learning that I haven't really gotten too into it to describe in this video. But you can also see the difference between doing this kind of hyperparameter search between the L2 norm and then the tau parameter used to smoothen out the vector similarity, and how it results in pretty different performance. You can see the difference between 64.4% accuracy to something like 58% with respect to searching through these different hyperparameters. The SimCLR algorithm explores the composition of data augmentations that are used to form these pairs for doing contrastive self-supervised learning by passing an original data point through two separate data augmentation functions and then comparing the representations that are used from separate projection heads from the representation into the space that is used to do the contrastive loss function. They also show that unsupervised learning benefits more from scaling up than supervised learning with respect to model size, batch size, the training epochs, as well as things like the data augmentation strength. And they also showed that the performance benefit of doing this difference between the normalized cross-entropy loss with adjustable temperature, this kind of function shown previously, works well on this contrastive learning task in the SimCLR framework. Thanks for watching this explanation of the SimCLR algorithm for representation learning on unlabeled data by defining this contrastive self-supervised learning task and exploring the importance of having a separate projection head, the composition of data functions, the scaling of unsupervised learning, and miscellaneous other things presented in the SimCLR paper. It's really interesting to see the performance of unsupervised learning come to reach this threshold of performing the same classification accuracy as a ResNet 50 trained with supervised learning on the same data set. I also think it would be really interesting to see this algorithm scaled to larger data sets like JFT 300 million, because that's kind of the point of these unsupervised learning data sets, is to exploit algorithms, is to exploit these massive data sets that you can get from, say, scraping the web or something like that. Thanks for watching, and please subscribe to Henry AI Labs for more deep learning and AI videos.